All right, so today I want to start a new set of slides, and it'll be a good segue. It'll be a good thing to come back to when you take CSCI 41, because I know most of us are going to go and take that class next. This is a lot of CSCI 41 topics at a CSCI 40-ish level, so that's kind of nice. All right, the first thing I want to talk about is searching, because what do? Like, you're a computer scientist, you're making programs. Pretty much every program at the end of the day takes in a bunch of data, and you care about finding a piece of that data, right? Like Canvas, for example. All of your grades are in Canvas. You want to go and look up your midterm 2 grade. Like, that's a searching process. Everything inside of a program usually involves searching somehow. So, let me teach you a few common searching algorithms to find something. Say you've got a bunch of data in like an array. Got a bunch of data in some big long array, and you want to know, like, is 42 somewhere in this array somewhere? There's an algorithm for that. I think you can probably come up with one yourself. But these kinds of algorithms will, they'll work regardless of the data structure you're using. Like, there's always a concept of searching. Like, is there a 42 in this linked list, which you guys now love or hate because you had to work on it in your textbook. So searching is a process that we should care about as computer scientists. We need it. Everybody wants to search for stuff in our programs, okay? That's part of a program always. So the easiest way to search for a number is to do a process called linear search, all right? This is like the naive way. This is the way that would make sense. Like, if I ask you to go implement a function that searches for something and finds it, you will probably come up with this thing called linear search, all right? Say you've got a vector, and you have, I don't know, a bunch of jumbled things. 8, 6, 7, 5, 3, 0, 9. And you got a value you'd like to search for, right? Let's say I'll call it val to search for. And you want to search for 3. I care about, is 3 somewhere in this array? I need to know right now. Somebody tell me. And so that's an algorithm for all right, somebody gives me the 3, the vector. I go through every index, right? That's the easiest way to find things. All right, I have all these indices. I'll just search them from left to right. 0, 1, 2, 3, 4, 5, and 6. And hopefully I'll find the 3 somewhere. That's a searching process, right? That's called linear search. You have to check every index if you have no guarantees about where the 3 is. It could be at the start, it could be at the end. You're not sure. So you have to go through everybody. So we call it linear. You're going through in a straight line this entire vector. Right? That's called linear search. And so it takes the vector, it takes the thing you're searching for, and it gives back an integer. What we're going to do in linear search is, if we find the thing, we will give back the index where we found it. So we found the 3 eventually. We'll give back 4. That's where it lived if you want to go and change that index now, user. Okay? So that's what we'll do for that. But if you're searching for a number that doesn't exist, like 42, you'll go through the whole thing, right? It could have been anywhere. You'll end up not finding it at any index. And then at that point, you have to still return an int. And so we'll choose -1 to return in that case, because -1 is an invalid index. It's never an index in any vector, okay? So that just means we didn't find it. And yeah, linear search is the best possible algorithm that you could possibly do to search for something in a jumbled vector. If you have no guarantees about where anything is, you are forced to use linear search, and you can do no better. It could have been at the front, could have been at the end, could have been in the middle. You're not sure. All right, so let me implement linear search. It's just going to be a simple for loop, okay? So we'll start a little searching library too, searching.h, searching.cdp, and then a main function that uses it all. So let's start the library. Searching.h, include our header file guards. Whee! And then I'm going to use vectors, so I need vector here. And then I would like this function, please. And remember, in a header file, you can never use namespace standard, because that would use it for whoever includes you. We don't like that. So it's got to be standard : vector. Events, I'm searching through that v thing for some value, and I'll give back the index where I find it if I can find it. Okay, so there's that. Let's do a main.cbp file that includes this library. Question first. Oh. All right. Include searching.h. And let's we get vector out of that, don't we? So I don't have to include vector separately. That's pretty nice. Part of the library. the library will include vector for me. And now I can make one. Vector int v equals, same one. And I will see out the result of linear searching through v for the number 3. Should give back 4. The index was 4, right? And then we'll search it for 42, and it should give back -1 once I get it working. Okay? So now let's take this library, and we'll implement it in searching.cdp. And I guess I need to steal this bit. There we go. Boop. I can use namespace standard all day long. Customarily, you should include your header file. Include searching.h. And we actually need it because it's going to include vector for us. That's perfect. You can use namespace standard all you want in your implementation file, so I don't need the standard : here. And then now my job is to just I got a vector, I got to go through it looking for this value. All right, so go through every index from left to right. It's the standard order, right? Looking for val to search for. There. Okay. And so it's just going to be a loop. For int I equals 0, that's the first index. I is less than v.size, last index. I plus. And we'll just check, all right, I'm at v at I right now. If v at I, if that's the thing I'm looking for, we're good. I found it, right? So if that's true, I found it. And my job is to return the int, which is the index where it lived, and that's I. Return the index where it was, so return I. All right, and then if this loop sadly completes without finding or returning anything, then we get down here. If we get here, right, the loop stopped, we never returned found the thing. If we got here, we didn't find it. Sad face. All right, so we'll return a special value for an index that's an invalid index, -1. Okay, if we didn't find the thing. And that should do it. Any questions about that? Does that make no sense? Linear search. Left to right, looking for something. If there are duplicates, it will find the leftmost thing, won't it? Because it's going from left to right. It'll stop the second it finds one, and it's working its way from left to right. So it'll find the leftmost one. And yeah, I've got this library now. I've got the main file using it. I've got the header file declaring this nice function that I'm implementing, and then I've got the implementation of it over here as well. All right. So they're all working together. Let's compile them. G++, give all the implementation files, and what do I want to call this? What let's call it? Let's call it searching this time. Why not? That's searching, so I should see, right? Index 4, that's where the 3 lives. 0, 1, 2, 3, 4. Bam, here's the 4. And then -1 because we didn't find the 42. Cool. So, yeah, I think the relevant one to look at is that one. Does that make enough sense still? This is a very simple loop, right? But it's an idea. It's a new idea. We want to search through this vector for something. This is a standard algorithm, linear search. All right. And now I have just a quick question for us. We don't have to go into groups or anything, but let's say we have some guarantees about our numbers. That will lead to a faster algorithm to search for some things. Let's say it will have to do with sorted numbers. So it actually, the next algorithm I want to teach you has to do with that guess the number game. Let's say that I have, I've picked a random number, right, between 1 and 100. Whee! This is my question to you. Somebody tell me. The second I say that, I have picked a random number between 1 and 100, what should be the number you guess first? 50. Why? Yeah. Yeah, any other thoughts? Do we agree that 50 is the best one to try? Do you have any alternative arguments as to why it's a good one? Can we expand? Yeah. Good, that's a good thought. I like that. So we want to choose 50 first because we have no control over this random, you have no control over the random number that I'm thinking of, right? No control at all. And so the goal of, the reason you'll guess 50 is because you're hedging your bets, essentially. No matter which number I was thinking of, even if it was a big number or a small number, you have just, the second I tell you what I need to tell you, if I say too low, right, you've just cut off this many numbers, haven't you? And that's much better than you guessing 75, and if I say that's too high, or sorry, if I say that's too low, excuse me, if I say that's too low, that means you cut off these numbers, my bad. Cut off all those numbers and it's somewhere up here. And that's a lot better than me, like you guessing 10 and me still telling you that it's too low, because now like you've cut off only 10 numbers and you have like 90 left to search through. Does that kind of make sense? You have the minimum amount left if you cut off half your search space like this, right? And so that's actually a new term. You cut off half of your search space. You're searching for this random number that I'm thinking of, right? And so you know if it's anywhere, it's going to be one of these numbers if I tell you that it's too low. And so now you know it's between 51 and 100, right? Which number should you guess next, right? After that, so like 75, right? That's going to be your next best guess, and that's, again, hedging your bets. It's like, all right, I know that the number, if it's between 50 and 100, or 51 and 100, really, and I guess 75, then no matter what, right, if you guess too high and I say it's too low, it doesn't really matter at that point. Like, you've cut off half of your space either way, regardless of whether the real number is over here or over here, because you have no control over that. Okay? So like if I say that's too high, like you'll know to cut off this one. And like now you know if the number's anywhere, it's between 74 and 51. So that's kind of the idea. No matter where the number was, it's always best to guess like this because you don't have control. If you make some weird guess like this, like the number could have been over here, right? And then you have way more than 50 numbers to look through still. All right, so it's always best to guess in the very, very middle, and that will lead to the answer the fastest. Right? Hopefully that's a little bit intuitive. Are there any questions about that idea? Because we're going to turn that into an algorithm. Right? Similarly, like I think that we're running this algorithm ourselves every day. We're not playing guess the number games, but like I don't know about you, but like when I turn on my shower, for example, I make the water as hot as humanly possible so that it heats up as fast as possible, and then I turn halfway, right? And I'm like, okay, is it the right temperature yet? Then I'll go in between, like it's probably too cold at that point. Now it's in between that place and super hot until like you keep on going in the middle of your options, right? Until you find your optimal shower temperature. So you're doing this in real life, and this will help us search for stuff as well. It leads to an algorithm called binary search, right? It's the same exact setup. It's going to take a vector or an array, doesn't matter, and it'll take a value that you're looking for, and it'll return the index where it finds it. But we have some guarantees about this vector. You cannot call binary search unless your vector / array is sorted, right? The second it's sorted, we can do this guess the number game, okay? Because that's going to give us guarantees about where something is, all right? So let's say, here's my example vector. It's going to be sorted this time. Let's say I've got 3 elements, or 6 elements, let's say. 1, 7, 33, 42, 55, 87. So let's say those are my elements. And let's say I want to search for is like 33 or something. All right. The optimal strategy for the binary search function is going to be the same as the guess the number game. What should we do? We should always check in the middle first. Okay? And because it's sorted, we're going to know a whole lot. We're going to be able to cross off half of the array / vector each time, right? So where is the middle of this? Let's say, just for sake of example, that 42 is the middle of the vector. Like from at the beginning of time, I haven't looked at anything in this vector, but I know it's sorted. I'm looking for 33, so I'll look in the middle. Let's say that 42 is the middle, for example. And so I'll compare 42 to 33. I'll notice that the thing I'm looking for is smaller. And so do you see, by doing one look into the vector, just in the middle, I can cut off half of it? I know it's never going to be to the right of that 42, because this vector is sorted. You see that? You didn't have that guarantee for an unsorted vector. So now I know if it's anywhere, if this thing is anywhere at all, it's between here and right here. Because we just checked 42, it wasn't 42. Okay. And so now I have a smaller array. I have a smaller space to search through. We call that the search space. Okay. I have a smaller search space, and I keep playing the same game. Right? What's the middle of this? Well, it's going to be the 7. Compare the 7 to the 33. Oh, okay, 33 is bigger, so I need to look to the right of this. So I can cut off this. And then you've just honed in on exactly where it is. You know that if it's anywhere at all right now, it's between here and here. And so your next guess, you go in the middle of that, which is that index, and you'll find the thing. that make sense? And so maybe this is a bad example because it took us 3 comparisons to find this, but for a size, let me just tell you, let's say that we've got a size 1 million vector that's sorted, all right? Log base 2, 1 million, and you're searching for something in that sorted vector with this binary search algorithm. It will take you, oh wait, sorry, log 2, no underscore. It will take you no more than 20 comparisons to find the number if it's in there, if it's size 1 million. Whereas for linear search, you'll have to look through 1 million elements, most likely. 20, only 20 with binary search. Because exponentially quickly, you find the thing, all right? You're cutting off half and half and half and half. And so like the answer is like, I used the logarithm to find that answer, okay? That's the goal. Does that process make enough sense? Do you think you could code that? It's a cool one, all right? So let's see. Let's go through it a little bit more in detail. Let's try to think about how we're going to code this out. Let me draw the vector again. So your search space gets cut in half. It halves each time you make, you look at something. You guess that it's here, and maybe it's not there, but you have some more information the second you guess. You look in the middle. Oops. We've got 1, 7, 33, 42, 55, 87, and these are indices 0, 1, 2, 3, 4, and 5. And let's say the value that I'm searching for this time, let's say it's 55, just for an example, okay? So here is what we must do, all right? To code this up, we need to keep track of what our search space is. Where in this vector do we think this thing could be? So at the very beginning of time, it could be anywhere, right? It could be at index 0, it could be at index 5. We're not sure. We just know the vector is sorted. We haven't looked at it yet. 55 could have been the biggest thing or the smallest thing. We're not sure, all right? So at the beginning of time, we're going to set some, they're not really pointers, but you can think of them as pointers. They're just like going to be int variables that keep track of which, like the lower and upper index of my search space. So like the lower index, low, I'll call that, is 0. Index 0 is the smallest index where this 55 could be, and then high will be 5. The highest upper index where the 55 could be, I haven't looked at anything yet, could be anywhere. It's between 0 and 5 though. All right. So at the very start of time, your low and high indices, your search space is the whole vector between index 0 and size -1. All right. So that's how you start those, and then you start looping. You keep on looking in the middle of your search space and changing it, cutting off half of it in the right direction. All right. So you check now the middle element between low and high. So what's your midpoint? So my first guess, my first index to check is the middle of my search space. And I'll calculate that as an index. I'll calculate it as 0 plus 5, right? The average. It's the middle of 0 and 5. 0 plus 5 over 2. We'll have to use integer division. So it will end up being 2. And so the midpoint will be this index. That's going to be the first index that I check. Right? I'll call that mid. Does that make sense? I'm looking there first, and I'll compare the thing I see there to the thing I'm looking for. And, oh, the thing that I'm looking for is bigger. Yeah. So that means if it's anywhere, it's between here and here. So my high index is fine, but my low index needs to change. Does that make sense? That's going to change the search space. That's how I'm representing my search space. All right? And so I have just cut off half of my vector now. I know, based on my comparison, that it could not possibly be, the number I'm looking for could not possibly be in any of these. All right? And so I'll keep high at 5. It's still high. And then low will be index 3 now. And then the next round of this loop, right? The next round of the loop, we used mid to like set things. We set low to be what? It wasn't the 33, so it's going to be mid plus 1, so that's 3. Okay, that's how you reset it. And now this is my new search space. Search from here to here. That's where the thing could possibly be, if it's in there at all. All right. So what's the midpoint of that? I think you can imagine whatever it is, it's going to be that index. And then you look and you compare 55 to the value you're looking for, 55. And you're like, bam, I found it. So you only need to do 2 comparisons, look at 2 indices, and you found the 55 that was way over here. Do you see the appeal of binary search? It's much, much faster than linear search. I can't draw 5 today, it seems. Does that make sense? So that's the process. You keep doing that in a loop, changing your search space, making it smaller and smaller and smaller, homing in on where that number should be, if it's there at all. All right. It is, though, possible that the number you're looking for is not in that vector or that array. All right. In that case, low and high are going to change in weird ways. All right. The second you don't find something, what's going to happen is that like low and high will pass each other. Like high becomes smaller than low. All right. That's what will happen. And when you don't find something, and when that happens, that means that like your search space is empty. Like if it's not in there at all anymore. It's between index high at the minimum and low as the maximum, and like that makes no sense. All right, so that means you didn't find the thing. And yeah, each time you do this, you're cutting off half of your array. You're zooming in farther and farther and farther. All right, so it's so much faster than linear search. It's beautiful. All right. So let's go through an example maybe of not finding that like low and high will pass each other. It'll look a little weird, but like that's going to be what we use to notice that we're done. All right. Either you return, you found the thing, or like your low and high pass each other, and then you need to stop. All right. Zoomed in version of this vector: 1, 7, 33, 42, 55, 87. At indices 0, 1, 2, 3, 4, and 5. And let's say that I'm looking for a value that's not there. Let's say I'm looking for 12. All right. So let's see what happens. So the very first time I do anything, what's my search space? The low index is 0, the high index is 5, just like the whole vector is my search space. Could be anywhere. And then my mid index, right? My first mid is going to be 5 plus 0 over 2 integer division. So this is my mid 1, because I'm going to have more midpoints. That's my first midpoint, and I'm going to compare the 33 to the 12. Okay, I'm looking for 12. I see 33, so I know that if this thing is anywhere, it's not over here. So I just cut off even more than half of my vector right now. I know it's not over here, and so it's going to be between here and here. So if you notice that something that you're looking for is smaller than what you see, then you're going to change high. See that? You're going to change high, keep low the same. High needs to change now to be mid 1 minus 1. That's where it needs to go now. All right. So this is now high 2. This is my search space. Does that make sense? What I just did? That's the kind of comparisons you'll be doing. And now I need to find the middle of this search space between low and high 2. Those are my current indices. So 0 plus 1 over 2, integer division is going to be index 0. And so this is my second midpoint that I'm going to look at next. This one. This is my mid 2. Okay, that's how the algorithm is going to unfold. And let's see here. What do I want to compare the one that I see to the 12 that I'm looking for. And I'm going to notice that, okay, the thing I'm looking for is bigger. All right, the thing that I'm looking for is bigger. And so I'm going to change my low index. All right, let me prove that to you. So let's say I'm comparing the 1 against the 12, and I know that it's bigger, so it must be past that index. And let's say that this is your search space between low and high right now. This is kind of the idea. Here's your midpoint. There's your mid. If you're looking for something that's bigger, then that means it's between here and here now. Does that make sense? So it's the low that changes. The low needs to become the mid plus 1. And that's what we just noticed. That's what needs to happen right now. So, all right. Index 0 did not have the thing. It was too small. I need to look to the right. And so that means my low index needs to change to be mid 2 plus 1. All right. So that is my new low index. High is staying the same when I'm looking up to the right. So let's see. That's low 2 now. So now my search space is low 2, high 2. Between index 1 and index 1. If it's anywhere, it's right there. Okay, does that make sense? The way the algorithm is zooming in. It's cut off a lot of the array, or the vector. And like, if it's anywhere, it's right here. So that's, well, we're going to calculate the midpoint of the search space, which is a size 1 search space. 1 plus 1 over 2 is 1. And so this is my third and final midpoint, right? This is mid 3, okay? This is mid 3. And again, the same thing's going to happen. All right, I'm looking at the 7, comparing it to the 12. What I'm looking for is bigger, and so we know that when I'm looking for something bigger, I change low. I change low to be mid plus 1. It has to be past that if it's anywhere in this place. All right, So that means my new low better be mid plus 1. So mid was 1 plus 1. This is low 3. It makes it index 2. Does that make sense? So low 3 has now, like my current low index, my current lower bound of where this thing could be, has now passed the high index. Do you see that? That is how it will notice that the thing is not there. And you'll check for that, and you'll stop your loop, because otherwise you just keep going forever. That's how you know when you're done and you didn't find the thing. That's what it means for your search space to be empty. It's between high and low in that order. There is nothing in that order, all right? So that's the secret, okay? So let's see here. I guess let's program this now. Let's program this process. Are there any questions about the diagrams first, though? All right. So let's add, let's go to the header file, I guess, and we'll add a new copy for binary search because it looks exactly the same, just a different name. Let's see. Header file, binary search. So I got that, and then I guess I do need it. Let's pretend we have it. Let's call it. I need a sorted vector now, though. Be like, let me copy all this. I'll call it V2. 1, 7, 55, 87. And then what did I do? Let's look for 33. Let's look for the 55. And let's look for 12, something that does not exist. All right? And we're going to call binary search. That one. Cool. So now it's our time to implement this thing. All right, so linear search and binary search are on the outside, they're the same. They both take vectors and look for something, but they do it in a different way. All right? So let me just delete everything out of here. We'll start fresh. All right, with binary search, what we got to do is initialize our search space. Initially, my low index is 0, my high index is size minus 1. The whole vector is my search space. It's hopefully somewhere within there. All right, initially, I got to look through the whole thing. The search space is the whole vector v. I know it's sorted because you can't call this unless it's sorted. And so my low index will be 0, and my high index will be size minus 1. Okay? And then I would like to keep searching as long as I have a valid search space, right? Keep searching as long as there's a search space to look through. I know what it means to have an invalid search space now, right? That's when high is past low. Or sorry, low is past high. Low is bigger than high. So we're good. We're good with the search space as long as low is less than or equal to high. It's okay for it to be equal to, right? That's fine. But as long as low is less than or equal to high, we are good. Otherwise, we need to stop. So while low is less than or equal to high, I have a valid search space to look within. And what do I want to do right now? I have some lower index and some upper bound index where this thing might be. I want to play the guess the number game. I want to look in the middle. I want to make a midpoint. Int, my current midpoint is the average of low and high, integer division. And so that's the index of the midpoint. And let's also save the value. The value at the midpoint is v at that index. Okay? So now I'm going to compare this value to the thing I'm looking for. Okay? So let's check. So if the value I'm looking for is smaller than this value that I see at the midpoint of my search space, what do I do? Where's an example of that? So if the value that I see that I'm looking for is smaller than the mid-val, that was the very first example here, wasn't it? That was this one. Oops. So I saw 33 and I was looking for 12. What do you do in that case? So low is this one still, high is this one still. Well, if I'm looking for something smaller, that means it's high's job to change. Low doesn't need to change. It could still be at index 0, but the upper bound index where it could possibly be is mid minus 1. Does that make sense? That's the new high. That's that example. So, okay, if the thing I'm looking for is smaller, then I need to search to the left. All right, so the value that I'm looking for is smaller than what I see at the midpoint. I need to look to the left. All right, and so what that means is I'll change my high index. Like we were saying, I saw 33, I wanted 12. I knew it's got to be between here and here. Low doesn't need to change, high needs to change to mid minus 1. Right? Does that make sense? You just got to draw the pictures and then that should work. Right? Else if, right? What if val to search for, if the thing I'm looking for is bigger than mid val? What do I do in that case? Right? What does that mean? So, okay, what example was that? So that's like here, we're looking for the 12 and we see 7, all right? So my search space is between what, here and here. I'm looking for the, or no, yeah, let's say it's like that. I'm looking for the 12, I see a 7, and so, okay, if this is my midpoint, I know if I'm looking for something that's bigger, then that means my low needs to change. Going to be, it was not up to here. It was like mid was way too big, and so wait a second. Sorry, mid was way too small. Excuse me, and then I need to look to the right of that. So if it's anywhere, it's to the right of this thing that I'm looking at right now. So I need to change my low index. Okay, and actually maybe this one's the better example. Yeah, this one's probably better. I'm looking for a 33, right? 33 is at my midpoint, but I'm looking for 55. I compare. 55 is bigger. So if it's anywhere, it's between here and here. So the high doesn't change, but the low changes to mid plus 1. Okay? So when in doubt, draw it. So that is the exact opposite of this. So the value I'm looking for now is bigger, which means I need to look to the right half of my search space. So low needs to change to mid plus 1. All right? It's just like the exact opposite. We still good? I have to be very careful with my words. This is a little tough to explain. So, all right, those are the hard cases. Else, if it's not less than and it's not greater than, it was just right. It was equal to. So if we get to this else case, we found it. We found what we were looking for. Where was it? Our job is still to return the index, right? The index where we found it. And we were looking at mid-val, which is at index mid. That's where it was. It was at index mid, so I'll return mid. Okay, I have to zoom out a little bit probably. So that's the loop, and the loop may stop though. So this will work. If it eventually finds it, it'll get to here, this else case. But if it's not in that vector, the loop will stop it. So here's the end of the loop right there. That's the whole loop. But if we get to the end, right here, if we get here again, that means low past high. Low must be greater than or equal, or strictly greater than high right now. If we get here, low past high, and so that means we have an invalid search space. The thing we're looking for is not there at all. We didn't find it. So sad, and we'll return -1 to represent that idea. All right? And so don't go to that index. It's an invalid index. Okay, so that's binary search in a nutshell. You start your low and high. As long as your search space is valid, look in the middle, compare against what you see, and then you're going to cut off half your search space each time. If you're looking for something smaller, your high needs to change. If you're looking for something bigger, your low needs to change, right? It's always relative to mid. It's never mid. It's always mid minus 1 or mid plus 1 because we just compared against mid. It wasn't right. And then if it was ever equal to, there's my answer. Search space becomes invalid, -1 time. Okay? So that is it's a fun algorithm. It's a little complicated. It's a good one to study. Are there any questions about this code? All right, so let's run it. Let's see if it works. So here in main, I'm calling on a few things. Let's see if it's happy. Oops. It would appear to, I think it's unhappy. I did something wrong. Because I'm searching through V, sorry. I need to search through a sorted vector with those values. That'll do it. There it goes. All right, so 33 is correctly found at index 2. 55 is found at index 4. 12, correctly, we stopped the loop because we couldn't find it in between 7 and 33. The indexes of my search space become invalid, and I give back -1 correctly. Cool. So it's working. It's doing the right thing. And that is going to be the code to study for it. Beautiful. Still good? So this binary search style process, like, It comes up when you're playing the guess the number game, when you're taking a shower. It is all over the universe. And I have a question for you now. All right, there is a way, all right, to do the same kind of searching, binary searching, to find the square root of a number. This is one way to calculate the square root of any number, to do a binary search style process. You're going to guess in the middle. You're going to have a search space. You're going to guess in the middle. And you're going to check your guess and update it. All right, so what I'd like to do is give you this question. Maybe I think we can go to the written nice page. Please do attendance as well. Stop that. But you guys can work together, and you can write a little post. And here's what I'd like you to think about. All right, I'll give you the actual algorithm in a second. But let's say we're trying to guess the square. We're trying to figure out. We're trying to accurately solve for the square root of 49. All right, and we have some search space. And let's say we've made a guess based on our search space that, all right, I am going to guess that the square root of 49 is 5. Okay, we know that's not the answer. But the question now is, how can you figure out that that wasn't the answer? You're trying to program square root right now. You do not have access to the answer for square root. So try to think about, with the people sitting next to you, how would you figure out, like, was my guess too low or too high? How would you do that without having access to square root? I just know I'm trying to take the square root of 49. It's my job to calculate it. I'm guessing that it's 5. How do I know that that was too low, right? Think about it and write it down, please. How could you figure that out without knowing the square root? How do you know? It'll give me another minute or so. Or you just tell me in English. How do you know? If you can't do square root, what would you do? How do you know it's too small? All right, I think that was enough time. Let's take a look and see what our thoughts are. How would I compare if I don't know how to do the square root? Like, my job is to calculate the square root, so I don't have access to that. How would I know that my current guess is not too big? Dun dun dun. Yeah, good. You're gonna compare 5 squared. Awesome. You can do multiplication all day long. That's fine. Good. It looks like we're getting it. Very nice. Good job, you guys. All right. So, yeah, the secret is, if I can't do square roots, I'm going to square this equation. And it's still an equation, isn't it? Now I have 49 to compare with against 25. And that I can do. And 25 is small. It's too small compared to 49. And so my conclusion is my search space is a little, like, I want to zoom in on the right answer. So I want to move my search space to the right. Is that how you spell conclusion? Conclusion. I want to guess higher. So I have to do the equivalent of, like, change my low. Okay, so this is going to eventually be a lab for you. It is a somewhat common interview question, actually, to do this kind of, make this kind of function that calculates square roots by doing this binary search process. And so you'll be ahead of the game once you do this. But in a future lab, maybe not this one, I can't remember, I'll give you this function to write. You will create your own square root function using binary search. All right. So given some double, calculate without using the math library the square root of an arbitrary double number. All right, as long as it's not like, as long as it's bigger than 0. Okay, so here's what you do. You're going to use binary search. You're going to do a bunch of guessing. All right, you're going to make a guess for your square root, essentially. How do I want to do this? I think I do want to draw it in a certain way. So like, what you'll do is like somebody asks for the square root of 49. So they'll give you 49 to your function, and you have to set up a search space. So based on the graph of square root, you know, right, that the square root, the answer for this square root of this number, the smallest answer it could possibly be is 0, right? That's my lower bound. That can be your initial lower bound. That's fine. And then your first upper bound guess, it can be a bad one. Let's just say that it's 49. Like, we'll guess that, like, all right, wherever the square root is of 0 and of 49, it's between 0 and 49. Does that make sense? That can be your starting search space. You do have to be careful. You have to make sure your search space contains the value, though, because what I'll say is, like, your search space should be, like, your upper bound should be the maximum of 1 in the number. Because what if somebody asks for the square root of 0.25? Does anybody know what that answer is? Off the top of your head? Oh, sorry, square root. It's bigger than the original number. Okay? So you do have to be careful. Like, you can't set up your search space. Oh, okay, the answer is somewhere between 0 and 0.25. That's not true. So it has to be like, you have to do some extra calculation, like the maximum of 1 in the number. So then you can just be like, all right, instead of that, let's start my search space from 0 to 1. So, like, you have to start your search space. As long as it contains it, the algorithm that I'm about to teach you, the binary search style thing, will find the square root. It's really cool, all right? So, let's say that we would like to calculate the square root of 2, all right? So that's going to be my example that I'm about to draw. Let's say we want to calculate the square root of 2, and so we're going to say, okay, whatever it is, it's between 0 and 2. That's my answer, all right? And so let's kind of draw the graph of square root and try to figure out why this is going to work, all right? Whee! I gotta be very, very precise right now. All right, so the graph of square root looks something like this. Whee! And we know at 1, 1, then that checks out. But any square root for like 0.25, it's bigger. It's like 0.5, so it's not to scale. But you kind of get the idea. There's like 2 or something. And we'd like to find the square root of 2, right? We'd like to find this point on the graph, which was like 1.4 whatever. Okay, so there's 1, there's like 1.4-ish, there's 2. My best scale, okay? So that's what's happening. And what we're going to do is we're going to start a search space like this. We're going to say that, all right, wherever this thing is, it's between 0 and 2. So my low starts out at 0. My low, for where I think the square root of 2 is going to be, sorry, low is 0. Low is right there. Let's just draw an arrow maybe. And then my high, my upper limit for where I think the square root of 2 should be is 2, and that's fine, right? It's within that range. And now I'm going to make guesses. I am going to check the middle of my search space, aren't I? What's the average of 2 and 0? It's 1. I'm going to look at 1, right? Compare, see if that's a good enough guess. Is the square root of 2 1? Question mark. So I'll square both sides, compare 2 to 1. Too small, isn't it? So that means I need to change my lower bound. Does that make sense? That's what we're going to do. And you'll cut off half of numbers, half of an infinity of numbers to get to where you need to go. All right. So you're just going to check if your answer is close enough. All right. You got to square the midpoint and see if it was close to the original number. And you're going to use doubles, so you have to do that double weird comparison, right? You have to do like, you got to square it, subtract it from the original number, and then take the absolute value, make sure it's small, and check for exact equality, right? So As long as like you keep doing it this way, eventually you'll find a number accurate to this many decimal places. All right. So if the mid squared was too low, like 1 squared was too low, is not 2. So that can't be the square. It's too low. That means my low needs to become, there's no concept of like mid plus 1 anymore. It's just like make it the old mid. So this is my mid, my original mid, right? My midpoint. Check that as too small. It's my mid 1. Let me write that better. Mid 1. And so now I know that if it's anywhere, it's between here and here. Okay, so I've just cut off half my search space. I will eventually find the answer this way. So now my search space is between here and here. And what's the middle of this now? It's 1.5, right? 1.5 is the midpoint of 1 and 2. I will square 1.5, compare it to 2. What is the answer? Whatever it is, it's too big, right? It's 2.25, so it's a little too big. And so that means I need to change my high, right? The mid square was too high, so I'll set my high to here. Like if it was anywhere, like the upper bound is 1.5 because that was too big still. All right, so that's a better upper bound. So I'll change. This is my mid 2, and so that's a new upper bound for me. Okay, that's how that's going to work. That's my new high 2 now. So now I know if it's anywhere, it's between here and here, between 1 and 1.5. So I'm getting closer and closer each time to the right answer. And then I'll check against 1.25. I'll notice it's a little too small, right? That'll be my next midpoint. And you'll keep playing this game until eventually, like, you zoom in far enough and you get to the right, like 1.4 or whatever, which is the correct answer. That thing. You'll keep on zooming in until you're within, like, whatever this comparison lets you get within, like, within with a precision of 4 decimal places. Okay? Does that make sense? You keep on cutting off half your space, comparing your answer to your midpoint squared. You'll eventually find the thing, right? And so you could code this. You could easily code this. Let's like walk through what should happen in your future code. You'll come back to this when I give you that lab eventually. Like let's say your x is 2. You're trying to calculate the square root of 2. And again, like let's set up a table. My initial values of low and high are 0 and 2. Like that's where the square root of 2 is. It's somewhere there. The midpoint initially of that is 1. And then what do I need to check now? I need to check, well, this is my guess for the square root of 2. It is too small. How do I know that? I'm going to square it, 1 squared, and compare it to 2. Is that close enough? No, it's too small. And so I need to make a decision. Decision is guess higher. And so to make sure my next guess is higher, because it's always the midpoint of something, I'm going to change my low index. So low is going to become the old mid. Now I'm going to guess between 1 and 2. And that's still correct, right? The answer is within within those bounds. Between 1 and 2, the midpoint is 1.5. That's my next guess. My guess for the square root of 2 is now 1.5. Is that a good guess? Is now the thing to check. So I'll square it. 1.5 squared. Compare it to 2. It's a little too big. It's a little too big, so I need to guess lower. Don't I? And to guess lower, it's always the midpoint where I'm using to guess. That means I need to change my high. Make it smaller than this. So the high becomes the old mid now. And I keep zooming in. I keep having a correct range that will hold the answer eventually. And it's getting closer and closer by half each time. Right? So now my new range is between 1 and 1.5. The midpoint of that is 1.25. I will check and see, like, that's my new guess, right? That's my guess for the square root of 2. Is that good enough yet? I'll square it. 1.25 squared, compare it to 2. It's a little too small. So I got to guess higher, right? Higher. And then that means I'll make this my new low. So the answer, if it's anywhere, it's between 1.25 and 1.5. And you see, I'm getting closer and closer to the right answer. If I just keep playing this game a few more times, I'll get this value accurate to more and more decimal places. Does that make sense? Any questions about that? So this is a binary search style process that you can use to find the square root of a number. It's not cool. Just because the square root is like this, it's like the answers for square roots, it's monotonically increasing. You're never going to, like, the square root graph doesn't look like this. You can't, like, jump around. You know that bigger things are to the right, smaller things are to the left. And so that's why you can play this game. And so you can do the same for, like, cubed roots. Any other kind of root. You're good. Just do the same thing. Okay? So, yeah, I think that's what I want to say. This is an introduction to a future lab. I can't remember if it's the one I'll give you today or not. Maybe not. We'll see. But that's a fun new algorithm to end on, I think. Are there any questions before I switch gears to something completely different? We'll remember this? All right. I would like to do a practical thing now. I like to teach you a concept called makefiles, which will help you compile things more easily. The second you make one of these things called a makefile, you're like giving the recipe for how to compile your program in a very efficient way. And so you never have to remember. You just type something very quickly and it will just compile for you. So this is going to automate compilation for us. So we have to go over again, like, what does it mean to do that? What does compilation even mean? So, okay, there's actually two steps, compiling and linking. Can't forget about the linking process, which I do gloss over. We do gloss over it as computer scientists. So the job of a compiler, if you want to be very correct about it, the job of a compiler is to take one single program file, one CPP file, into what's called machine code or object code. That's just like the ones and zeros that your CPU can understand, right? It takes one file. So like you give it, we're giving to G++, which is our compiler, and also our linker, we're giving it searching.cpp as well as main.cpp right now. We're giving it both of these files, and it's compiling them separately, all right? It's taking just searching.cpp, the job of the compiler is that, and it creates object code for that one file. And then in a separate round, it will give main.cpp to itself and create object code for that one file, all right? Once you have a bunch of those, you've got the object code for searching sitting around, you got the object code for main sitting around. G++ is just automating this all for us, but we need to know the nitty-gritty now. We have all these together. The job is now the job of the linker. The linker combines those separate things, right? With like libraries and stuff like IOStream has been pre-compiled. We need that. Vector library been pre-compiled for us. Like all those other things. We feed them all in at once then to the linker, which is also G++ for us, which makes this a little difficult to explain. And then only then, after that, once we link with all of our files as well as any libraries that we're using, and G++ will do it for us, then we finally have machine code that will run on our CPU that will execute our program, okay? Only then do we have our /searching file that we can go and run like that, okay? So that's the compilation process, and G++ is doing this all for us. We give it all these things, we tell it what we want it to be called, and it goes and it separately compiles, just secretly, searching.cpp and main.cpp into object code, just by themselves, and then it links them for us into the final executable file. That's what it's been doing, okay? We can have more control over that process, and we need that kind of control, right? Because imagine, one day, this will be true, you're going to be working on a giant project, right? In the real world, you have like thousands, hundreds of thousands potentially of CPP files that you're working on, and that compile your final like project that you're selling to somebody. Do you know how long it takes to compile 100,000 CPP files? It takes forever, all right? Even if you try to like parallelize it. You do not want to have to feed them all to G++ and have it recompile each one of them each time if you only change one thing, one line of one other file. Does that make sense? So this is going to save your life one day. We need to know how to do this separately, okay? If I change one file, like, do I really have to recompile all of them? Like, that's silly, right? Let's say I've got a bunch of things. I've got x.cpp, I've got y.cpp. They're all working together. That's supposed to be a y. Doesn't look like a y. I've got z.cpp. They're all working together. And when I say G++ on all these bad boys, what it's going to do is it's going to translate them all separately for a split second to machine code, object code, the ones and zeros that represent those particular files and all the code inside of them. And those are pieces of object code. We call those .o files usually. x.o. So x.cpp gets compiled by itself into x.o, y into y.o, z into z.o, and like G++ is just going to remove them for us later once it does its job. Because we've been doing it like this. Like give them all, it'll separately compile them, it will then link them into a final file that I have chosen to call blah, apparently, in this example. So it's going to link them all together, bam. That takes a while. The more files you have to compile, the longer that takes. And say you change just one thing. You change, like, I'm happy with everything except for one line in x.cpp. If you do it this way, G++ doesn't care. It's just going to recompile Y and Z as well and relink. And these are the bottlenecks. To do that compilation, if you had 100,000 CBP files and you only changed one, it would just, if you did it this way, it would recompile all of them into object code, and that would take hours, if not days. Okay, so that's unfortunate, and there's a better way. That's inefficient. Let's ask G++. Let's learn how to ask G++ to just separately compile things, and we'll tell it to link them after that. So here's the secret. All right, what we'll do is we'll add the -c to G++. -c just means compile this file only. Compile only. So if you give -c to G++ and you give one CBP file, just one, it will compile that into object code and it will keep it around. It will make this new file called x.o, which is the machine code form of x.cpp. So that's what we want. And then we can do the same for the other files, for y and for z. We'll have them from before. And then when we change the x file, we'll just recompile just it, keep the old ones the same, and that's going to save us so much time. So save us hours, if not days, if you compound that, right? So remember, the x.o is the compiled machine code form of just x.cpp. And then once you've done that, you can link them together. All right, linking is fast, compilation is slow. So let's do that for our library. So here we got all these bad boys. Let me remove everything, even the searching compiled file. So I'm just got the implementation files right now and the header file. So I will separately compile those. I'll say G++ -c main.cpp. And that's going to make main.o. See that? G++ compiled just searching.cpp. It's going to make searching.o. So here they all are sitting right there. And now I can say I can link them. I can link them together, and that's a quick process. All right. So to link, you just give to G++ all the .o files, and then you give -o what you want it to be called. Like you're good to go. That's not too bad, I hope, right? So that's the linking process. You've got all your things, you've got all your precompiled things now. Y.o, Z.o, and then you give it some final thing, you link them together. This is the linking process. All that machine code is being linked together. The hard work is over, and you're calling it, apparently, exec file name. Your executable file name, whatever you want to call it. That's the linking process. That's how you do it. You just give the .o files, right? Just like we were given just the .cpp files before. So, okay, I've got these .o files. Now I can say G++ main.o, searching.o, link them together in a final file called searching that I can then go and run. And then it works. Does that make sense? That's what you can do. That will speed it up. If you had 1 million CBP files, you just changed one, you just have to recompile that one and then relink everything. So let's make a change. Let's say, all right, I got main.cpp. Let's add a line to main.cpp. Let's be like, all right, let's binary search for, I don't know, 87. How about that? And so now I have not messed with the searching library. It has been precompiled. It's right there. I have not touched that. That can stay the same. But I do need to recompile main.o because main has changed. Okay, main.cpp has changed. So I'll say G++ -c main.cpp to make main.o again, and I will relink it with the old searching.o. I've saved so much time if there were 1 million other files. G++ give the two .o files, however many there are, call it searching again, and that'll call the linker. That's a much quicker process. Compilation is the bottleneck, and there it is. It's finding that 87. All right, so I've separately compiled things. Are there any questions about that? Yeah.
What if you have like 100,000 .o files?
Exactly. You will end up having 100,000 .o files. That you can't get around that.
Okay, so you will have to type it or something will do it for you.
I'm about to show us a way to automate it. Yeah. So you do want to do it this way though. If you have 100,000 CBP files, you need to make 100,000 .o files so that it will compile fast. You do need to separately compile things, but there's a way to save your fingers. Okay, and that is called makefiles. Okay, so this is actually it's kind of a new programming language. This is the makefile language. It's different, right? So what a makefile is this is an example one. It's what it looks like. What it does. Let me get rid of these underlines. I don't like them. A makefile is just a file, and it's a file in your directory called exactly makefile with a capital M. It's weird like that. No extensions, just makefile. That's all it's called. This is a file called makefile. This is what it's called. It's makefile is its name. No extension. And then this is its contents, right? And what it has is a bunch of little recipes for how to compile your stuff separately as well, right? So like, I'm going to teach you what all these means. Like this is a recipe to make main.o. This is a recipe to make foo.o. This is a recipe to make something called prog that links together those things by running that line of G++. So the idea is like you say once and for all in this thing called a makefile how to make your program, and then you can just you can hand off the compilation process to it. It will do it in the most efficient way for you. Okay? So that's the goal. That's where we're going. So what a makefile is it's got a bunch of these things called rules. I call them rules, right? And they're each little recipes for one thing that you would like to build, okay? So here's kind of what it looks like. It's always the thing you want. It's called your target, like the thing I'm aiming for. Then you give a colon, and you space separate all of the ingredients or requirements. What do I need in order to make this thing? What needs to exist first? These are usually file names. And then you tab over. Your editor should be doing this automatically if you're using a good one, like Vim or something. And you tab over, and it has to be a tab. It cannot be spaces, by the way. Makefiles are weird and antiquated. It has to be tabbed over, and then you put on that same indented line as many lines as you need to make, using these things to make the final thing you wanted. Okay? Usually it's like calls to G++. Like these are command line commands that go here. That's what you do on the terminal to make those things. Okay? So my silliest example is let's make a makefile for a peanut butter and jelly sandwich. Okay? So like, what do I need? I need a rule for a peanut butter and jelly sandwich. I'll call it PB_J. That's my target's name. And then put a colon. What are my ingredients to make a peanut butter and jelly sandwich? I need a few things, right? So I'll space separate those. I need peanut butter. I need jelly. I need bread. I need like a knife. And you could write more, of course, right? But those are my ingredients to make peanut butter and jelly. And then what are my steps to actually go and do the thing? So I'll tab over, and then I'll write as many lines as I need indented to make, using these ingredients, this thing that I care about. Right? That's what a makefile rule looks like. It's like, all right, what do I gotta do? Open peanut butter and jelly jars. Get 2 slices of bread. You know how specific you have to be now when you're talking to a computer. Right? Eventually. I trust that you'd write the full thing. Okay? That is an example of one makefile rule. And the beauty of makefiles is you just say what you want. You say, I want peanut butter and jelly makefile, and it will go and find this rule, and it's going to go and it's going to look for these ingredients in your pantry or in your file system. And if you do not have one of those ingredients, this is the magic of makefiles. You just tell it what you want. It'll go in and it'll look through all these ingredients, and if you do not have one already, let's say you don't have peanut butter, it will go looking for a peanut butter rule. This is very powerful. So we'll go and look for one of these, and it'll make the peanut butter first, and then go off and do what you needed to do. It's like, how do you make peanut butter? You need peanuts. You can have another rule for that. Peanuts and a blender. Potentially salt. And then, like, what is your rule? You know, what's the recipe? What do you do with these ingredients to make this thing? You blend peanuts, right? Blend peanuts. Put in jar. So this is going to be very, very powerful. I'll give you an example next time, of course. But this is cool. I hope you agree. And yeah, so it'll go looking. Like you tell it what you want, and it will go looking for all these ingredients. Only once it has them will it run the final rule. But if you don't have it, it'll go and it'll make peanut butter for you. It's really cool. And then, all right, how do you if you don't have bread, for example, what's the recipe for bread? What are the ingredients in bread? Like flour, yeast, salt, water, or just money. Money is an ingredient for bread. As an example rule, right? Go to store, buy bread. Now you have bread. So you give all these rules to make all these things, and then they'll all work together. Okay, that's kind of what a makefile is all about. So let's talk about how you would do this for actual programs. So it's always the name of the thing that you want. This is usually a file name that you're trying to get at, and then you have a bunch of requirements, which are also file names. These files must exist in order for me to make this thing. Okay, and then you tab over and you give a bunch of commands to make the thing. You might need multiple lines. But these requirements are like your ingredients. Those are your ingredients, And so for example, let's say I want to make main.o. That's my target now. I want to make main.o. What do I require to exist in order to make this at all? Well, main.cpp better be there. I need main.cpp to make this. That's my one requirement. Tab over. What do I need to do to take main.cpp and build main.o? I say g++ -c main.cpp. That is a correct makefile rule. Does that make sense? That's what we're going to do. All right. And here's what the rest of those kind of look like. You have them for all of your .o files, and then your final program, you call it something. You got some .os here, and then you say g++ to link them together. Like, I require to make this final thing, these .o files, they better exist. Go and make them if they're not available yet, and then link them together into the final thing that I'm calling this. All right. So I'll give you an example of this next time. But the beauty of makefiles is there's a program called make. There's a terminal command called make, and you just say make on the terminal. It'll look for a makefile, and you give it the name of the target you want, like make searching. And it will go and it will just run that final rule that you need. It'll build anything, any intermediate things that you need to, like the .o files. It'll build those if those don't exist. Or if something changed, it will recompile the minimum amount of things. It knows what has changed as well. Like, make files, the second you write one, it just will, in the most efficient way, compile your program. You never have to type anything out again except like a line that says make on it. That'll be really cool. Yeah, this is like the final, for this example, this is like the thing you would go and you'd run. Yeah, this is being compiled into a final executable that you could run, and it's called probe. But for us, it'll be like searching. That's what we'll do next time. That's the name of the thing that we wanted. We wanted something called searching. I can go and run like that. / searching. Yeah, good. Any other questions? All right, so I got a few things to give you guys today. That's where we'll stop for the day in terms of lecture. I have a few things to do. The first thing is I want to release an extra credit assignment that is going to help my counterpart, Professor Kearney, do some of his research. So, as you know, you are not allowed to use AI in this class, but I am finally letting you use AI. Get it out of your system, okay? So I'd like you to do the following. This will be very helpful, right? It'll be up to 1% extra credit. It will be due midnight on the 17th, so you have a little while, a little over a week. And here is the write-up. You just got to follow the instructions in the write-up. What you're going to upload is a PDF file. So you're gonna write some stuff down, and you're gonna talk to ChatGPT to have it do something, and we're gonna see how well it works for you, all right? Because certain schools, they are making like a CSCI 40 for non-majors class. So like they're teaching them how to like use AI to write programs. If that's not going to be your main job or something, just like to help you on the side. Like you guys, is probably going to be your main job. You have to learn how to program. But let's see how well this holds up, right? So I would like you to write some code that tests something. I'd like you to write some tests and then ask ChatGPT to pass the tests, essentially. All right? Here's the goal. You're going to pretend that you're not a programmer, and you're going to ask ChatGPT in English to solve a problem in C++. All right? You're only allowed to speak English to ChatGPT. This is your goal, right? If you want to do this extra credit. You got to keep talking to it, like keep correcting it, because it might be wrong the first time. Well, I tried this. It's going to be wrong the first time. Keep talking to it in English until it gives you the right answer. And your job is to make some tests up front to know when you had that right answer. Okay? Does that kind of make sense? That's what we're going to do. So here is the problem that you don't know how to write in C++, but ChatGPT will figure it out eventually. Here's the problem that I want you to solve. You need to make a function called this. You cannot give that to ChatGPT. You have to tell it, I would like you to make a function called convert that takes a string and returns a string. You have to talk to it in English. And here's what I want you to do. So create a function that takes a string, returns a new string, after converting all the characters between stars to all caps, right? So for example, if your convert function saw that string, hello world, I love CSCI 40, whatever, then it should return back this string. It's capitalized world, it's capitalized love CSCI. Does that description of the problem make sense? Because you have to describe that to an artificial intelligence now, all right? So the first step, though, is you need to know, like, when is the answer correct. So I want you to make first a file, make a brand new CPP file that has at least 10 tests in it, right, using assert true. So here's assert true. Before you talk to ChatGPT, make 10 assert true tests for this convert function. All right, that's what I want you to do to know like when it's got the right answer. You'll keep on trying it, right? So you'll use them to like, you want them to all pass. Once they pass, you can assume that like ChatGPT did the right thing. So for full credit though, I want you to check edge cases. So you can imagine like, what if the user forgets to give a star? What should happen? You can decide what happens, but you better make a test for it. Okay? Does that make sense? Don't just assume that the user is going to give you a good looking string with everything that is closed off. Okay? Like decide what happens when the stars aren't matched, create a test for it. So I want to see at least 10 tests for this convert function, just pretending you have it. But you're going to let ChatGPT write it for you. Okay? And then it's time. Right? You'll go to ChatGPT, you'll ask it questions using nothing but English. You have to talk only in English, please. All right? And tell it to write this convert function. You cannot give it any complete lines of C++. You have to talk to it in English. You've got to pretend that you are not a coder. Okay? We're going to see how well it works. It will eventually get it right. I tried this. Okay? If it makes a mistake, you have to correct it in English. Does that make sense? It's a little weird. And then, like once, eventually, it will give you code that passes all your tests, in theory, all of your good tests that test the edge cases and everything. At that point, you're done. I just want you to submit like your ChatGPT conversation as well as like your code. Okay. So your last step, once you got all that working, is submit your conversation, all your code, and then just like show me a screenshot of your tests passing as just like a big PDF file. All right, that's what you'll be turning in. All right. Does that make enough sense? So you're going to ask ChatGPT. You finally get to use AI. Just get it out of your system. You're going to talk to it in English, though. All right? And you're going to make sure it worked by making some tests. So just follow these rules. Let me know if you have any questions. Here's an example of what I'm looking for. All right? So I've asked ChatGPT to do something similar to one of our labs. Remember the FizzBuzzBaz? I told it to make it like a FizzBuzzBaz function, essentially. Like, all right, here's kind of what you do. I'm working on a computer science assignment, blah, blah, blah. Could you please write me a C++ implementation that does these things, right? Like a function called FuzzBizBaz instead of like just a full file like we were doing in the lab. We'll have it return strings if it works, and like the number n otherwise. So this is just an example of what you would do. And like here it goes. It's going to start doing those things. Boop. It's going to say some stuff, and like here's the code that it gives back. And then I'm going to have a conversation with it, because eventually I want this to be something I can copy and paste in my program after I've made tests. All right? So like it explains it, whatever. And then I noticed like something was wrong. Like, why did you include stream? So I told it, like, was that necessary? Like you talk to it in English, and then eventually it will tell you something back. It's like, oh, you know what? You're right. I didn't need that. And then here's the new code. So you're going to keep having that kind of conversation. And then I'm like, all right, can you please use namespace standard and like change the code to do that? Just like keep on asking it in English what you really want. And like this is a simpler problem, so it gets it right quickly. But like there's the final answer. It worked. And now let's make sure with tests, right? Whee. So here is, then you'll paste all your code. Like here I am. Here's the ChatGPT's code. Here are all of my tests with assert true. Got a bunch of them. Checking for edge cases like negative numbers. All right. And then here it is running them, and then I'll give a screenshot showing that they all passed. All right? So you're going to do the same for that harder question. Does that make sense? So yeah, that's worth up to 1% extra credit. You get to use AI for once, get it out of your system. Just follow these instructions and turn it in like a PDF in the same kind of style of this example. Okay. So yeah, if we're good with that, that's the first thing I want to tell you about. Next, let's talk about your next lab. So we do week 15, so you got a couple weeks to do it. And this will be lab 9. Not the square root one yet. We still need a recursion lab. So here's the recursion lab. Boop. Alright, so we got a bunch of recursive functions that I want you to write in this lab. You're going to get good at it now. Alright, so your first problem is to write a palindrome checking function. We know what a palindrome is, right? It's just a word that reads the same backwards and forwards, like race car is the best example of a palindrome, right? You read it forwards and backwards, it's the same thing. That's a palindrome. And then like ABA, these are also palindromes, right? These silly strings. But we're going to clean up the string that we're given as well. So we're going to consider like this string as well as this weird looking race car with capitalization and spaces. We're going to also consider them to be palindromes. Okay? So it'll be a two-step process for palindrome checking. So here's the header file. You've got is palindrome and then some other ones. I'll talk about the other ones. Is palindrome is the CPP file. You're going to need a little helper function to clean up that original string for is palindrome. It's not actually recursive yet. So you're going to need a is palindrome recursive function to actually do the problem. But your original call to is palindrome is going to clean up the string first, right? So this first function does not have to be recursive, but it will call your recursive palindrome checking function, okay? So like this is because the string might look a little weird. Like you might be given this string, which should be a palindrome, or that weird looking race car. Like what you should do is clean up this string, right? Take this string, make a new version of it that's cleaned up with no spaces. They're all lowercase or something. Like convert this string, for example, to like AAA, because then you can easily see that that's a palindrome, yeah? And your code will too. So like this is the one non-recursive thing. And then you call your is palindrome recursive function on that simple preprocessed string. It'll take the string and like give you back true or false, and that's your final answer. All right. So this is a helper function that kicks off the recursion. It's going to clean up the string. Okay. Does that kind of make sense? It's a little weird. You'll get it once you read the comments. So that's the first thing you do. That's your helper function. It's going to clean it up, and then it'll hand off the problem to the recursive part. Because palindrome checking is recursive. I have a picture for you. Okay. So that function, after you do that, down here, here's your is palindrome recursive. Check whether or not the nice pretty string that you were given was a palindrome. Return true or false. All right. So here's what you do. Can you find the smaller palindrome checking problem, the next smaller one, in the original biggest problem? Can you use my picture to find a smaller palindrome inside of a bigger palindrome? You see it? Stare at it. Stare at it until you do. That'll be your recursive case. Okay? And then what do you still need to check then? Well, what does the smaller recursive answer give to you? And what do you still need to check, right? It's going to be like, make sure that the outer things match, something like that, okay? So that'll be that. Think about the base case, right? There might be base cases. Yeah, there should be two base cases at least for palindrome checking. Like, which strings do you immediately know whether or not they're a palindrome? You don't have to do any checking at all. There's a couple of them, all right? Well, there's a few, but they'll all have things in common with each other, right? So think about that, and that will be the palindrome checking problem, okay? So I've got some tests for that already in test recursive funcs.cpp. Some palindrome tests, all these bad boys. It's like checking, making sure like these are palindromes, these are not palindromes, etc., etc. Okay, stuff like that. And so that will be what you implement there. So clean up the string, call your recursive function, let that do all the hard work. All right. Questions about is palindrome recursive? That's a good first one to do. And then I want you to do a sum digits recursive function. All right. This one's called sum digits. It's going to calculate, takes a number, returns a number. It's going to calculate the sum of all the digits in that number. So like if you were given 1,234, you're going to return 10 because 1 plus 2 plus 3 plus 4 is 10. Does that make sense? If you're given 123, you should return 6 because 1 plus 2 plus 3 is 6. And this is a recursive problem. Think about it. Here's the recursive case. Can you find, I've highlighted for you, the smaller summing digits problem. See that? You have to somehow convert your number into that number, though. Like the 4 is left over. You have to use that still. So think about that. And then also think about your base case. All right? What's it going to get down to once you keep doing this pattern? Okay? So that's going to be sum digits. That's got to be recursive. All right? The rest of these are all recursive functions. Does that one make enough sense? So you're going to stare at these pictures until they do. All right? That's going to be the goal. And then finally, I kind of did this as an example in class. Right? I gave you a C-string recursive function using pointers to move around and get to smaller strings. I'd like you to make the equivalent of strlen for C-strings, a string length function that recursively figures out the size of a C-string. So you're given a C-string, and you want to give back the size of it, the length of it. All right? So like if you're given the C-string ASDF, it should give back 4. So don't count the null terminator as a character. You're still going to look for it to know when the string is over, though. All right? The length of an empty string that just has the null terminator in it is 0. Okay? And so, yeah, you got to find the smaller string. Do you see how the size of the hello string is the same as that? and there's a smaller string length problem that makes it recursive. All right, and then think about the base case, like when do you immediately have the answer at your fingertips? You don't have to do any smaller answer searching. That's going to be your last recursive function that you'll implement. Does that make sense? Do shout out when you have questions. It's going to be a little confusing. It's going to take some head scratching to like understand these pictures, but once you do, you've unlocked the power and the magic of recursion, and that's what I want for you. Okay, so I've got all these tests to make sure they work, all the stuff that you're doing, and I think that's all that I wanted to say. Any questions about any of those pieces of code? Because the only thing that you're going to turn in then is your implementation of that library. Okay, you don't need to write any tests this time. Just get the ones that I've got passing. We good? All right, I think that's all that I wanted to say. Question? A palindrome is a word that reads the same forwards and backwards. So like race car, it's R-A-C-E-C-A-R, and then backwards it's also R-A-C-E-C-A-R. Forwards and backwards, yeah.